Somewhere in the galaxy tonight, there is an object the size of a city, spinning quietly in the dark. It is heavier than the sun, all of it, every bit of mass the sun contains, compressed into something you could drive across in under an hour, if driving across it were possible, which it is not. It does not glow the way ordinary stars glow. There is no surface fire, no slow churn of light pushing outward, just density, just weight, folded into a space barely large enough to hold a small city's worth of streets. It spins. Some of these objects turn hundreds of times every second, fast enough that a point on their surface moves at a meaningful fraction of the speed of light. And yet, from a distance, many of them appear calm, steady. A small point of light blinking with a regularity that puts most clocks to shame. Tonight we are going to travel toward one of these objects. Not quickly, and not with any particular destination in mind beyond understanding what it actually is. We will start small, smaller than small, in fact. We will start with a single atom, the kind of thing that makes up your hand, your pillow, the air settling around you right now. And from there, we will follow that atom all the way to the edge of what matter can become. There is no rush. The night is long, and the star will still be there when we arrive. Right now, wherever you are listening from, your body is resting against something solid, a mattress perhaps, a couch, the floor if you have drifted there during a long day, and gravity is holding you there, gently, without effort, without announcement. It has been doing this every second of your life, and it will keep doing it tonight and tomorrow, and for as long as you remain on this particular planet. Gravity, in the form most of us know, is almost embarrassingly mild. It is the reason a dropped spoon lands on the floor instead of drifting away. It is the reason rivers flow downhill, the reason your eyelids feel heavier as the evening goes on, the reason sleep itself has a kind of physical pull to it, a settling, a sinking, a being held. For nearly all of human history, this was simply what gravity meant. A constant, quiet pressure, something so familiar it barely registered as a force at all. Something that kept things in place, rather than something that could do anything else. There is a particular kind of memory many people carry from childhood, not a specific night exactly, but a kind of evening, lying on your back somewhere outside, grass or a blanket beneath you, looking up at a sky scattered with points of light. Not studying it, not trying to identify anything, just looking, the way a child looks at something too large to ask questions about yet. At that age, none of those points of light meant anything in particular. They were simply there, the way the ceiling of a room is simply there, steady, background, part of the shape of the night. It would be many years for most people before anyone explained that some of those points of light were not like the others, that hidden among the ordinary stars, the calm, slow-burning ones like our own sun. There are objects so different from anything on Earth that the word star almost stops being the right word for them. One of the strangest of these has a comparison attached to it that tends to travel from person to person, the way certain facts do, repeated at dinner tables, in classrooms, in late-night conversations, slightly different each time, but always pointing at the same impossible idea. The comparison goes something like this. Take an ordinary spoon, the kind sitting in a drawer in your kitchen right now. Fill it with material from the core of one of these objects. That spoonful would weigh billions of tons, not as a metaphor, not as an exaggeration for effect. Billions of tons in a space smaller than your palm. Most people who hear this for the first time do the same thing. They pause, they try to picture it, and then, almost always, they fail. Not because they are not clever enough, but because the human mind was never built to hold an image like that. We evolved to judge the weight of stones, the weight of water, the weight of another person leaning against us. Billions of tons in a spoon sits outside every scale we have ever needed. And yet, it is real somewhere right now. That density exists. Not as an idea in a book, but as an actual object, spinning in the dark, made of matter that has been pushed past every limit our intuition was built to handle. To understand how something like that comes to exist, we have to go somewhere smaller first, much smaller than a spoon, much smaller than anything you could hold. We have to go inside an atom. An atom is, By almost any honest description, mostly nothing. That sentence sounds strange the first time you hear it, because everything around you feels solid. The table beneath your hands, if your hands happen to be resting on a table, the wall behind your bed, your own skin. None of it feels like nothing, but shrink down far enough and the picture changes completely. At the center of every atom sits a nucleus, a tight cluster of protons and neutrons, holding almost all of the atom's mass in an extremely small space. Around that nucleus, at a distance that is enormous by comparison, electrons exist in shifting clouds, governed by rules that do not map cleanly onto anything in everyday experience. Here is the comparison that tends to stick. If you took an atom and enlarged it until it was the size of a football stadium, the nucleus at its center would be roughly the size of a single pea, sitting on the 50-yard line. Everything else, every bit of space between that pea and the outer edge of the stadium, would be empty, or close enough to empty that the difference barely matters. The stands, the field, the air above it, all of it would be occupied by nothing more than the faint flickering presence of electrons, which are themselves almost unimaginably small. So when you press your hand against a table, you are not actually touching the table, not in the way it feels. What you are experiencing is something closer to a conversation between forces. The electrons in your hand and the electrons in the table repelling each other, refusing to overlap, creating the sensation of solid contact without any true contact ever occurring. The table feels solid because those forces are doing their job extremely well. They have been doing their job, in fact, for as long as matter has existed in its current form. Every table, every floor, every body that has ever rested against another body has relied on this same quiet electromagnetic negotiation. Atoms staying at arm's length from one another, space holding its shape, solidity emerging from emptiness through nothing more than mutual refusal. It is, in its own way, a kind of agreement, one that has held for billions of years across every object you have ever touched without a single exception, until you get to the center of a dying star. There, the agreement breaks. Most stars, including the one our planet orbits, will never reach this point. Our sun is, by stellar standards, a fairly ordinary star, middle-aged, stable, burning hydrogen into helium at a steady rate that will continue for billions more years before anything dramatic happens to it. When the sun eventually runs low on fuel, it will swell, cool, and settle into a quiet kind of retirement. No explosion, no collapse, just a long, slow fade. But not every star gets to fade quietly. Some stars are born far larger than our sun, 8 times its mass, 10 times, sometimes considerably more. And mass for a star is not simply a matter of size, it is a matter of fate. The heavier a star is, the more violently it burns, and the more violently it burns, the faster it moves toward an ending that smaller stars never have to face. These massive stars live shorter lives than smaller ones, despite having more fuel to draw on. They burn through that fuel at rates that seem almost reckless, trading a longer life for a brighter one. And at the center of one of these stars, in the final stages of its life, something begins to happen that has no equivalent anywhere else in the universe. The atoms themselves begin to fail. Not slowly, not gradually, the way a fire dims as it runs out of wood. The failure of atomic structure inside a collapsing star happens on a timescale that is difficult to even describe in human terms. A timescale measured not in years or days, but in fractions of a second. To understand why, we need to follow the star's fuel all the way down. Through the layers it has been burning, one after another for millions of years, building toward an ending none of those layers could have predicted. Every grandmother who ever told a child to come inside before dark, every person who has ever leaned their full weight against a closed door without a second thought was relying on the same electromagnetic agreement. Atoms holding their distance, solidity emerging from empty space. None of them needed to know why it worked. It simply always had. Inside a massive star, fuel does not burn the way wood burns in a fireplace. It burns in layers, stacked layers like the rings of an onion, each one fusing a different element, each one running at a different rate, all of them held in a fragile balance against the relentless inward pull of gravity. At the center of that balance sits hydrogen, the lightest element, the simplest, and the first fuel any star uses. For most of a star's life, hydrogen fuses into helium, releasing energy outward, and that outward push is what holds the star up against its own enormous weight. Gravity pulls in, fusion pushes out. For millions of years, sometimes billions, the two forces hold each other in place, locked in a balance so stable it barely seems like a balance at all. But hydrogen does not last forever. When the hydrogen in a massive star's core begins to run low, gravity gets, for the first time, a small advantage. The core contracts slightly. That contraction raises the temperature, and at that higher temperature, helium, the leftover product of all that hydrogen fusion, begins to fuse as well into carbon. The star finds a new balance briefly at a slightly higher level of intensity. Then carbon runs low. The core contracts again, temperatures rise again, and carbon fuses into oxygen, and then neon, and then silicon, each new fuel hotter and more demanding than the one before it, each stage shorter than the last. The timescales involved are strange enough to sit with for a moment. Hydrogen burning in a massive star can last millions of years. Helium burning might last a few 100,000. By the time the star is fusing silicon, the entire process may last only a matter of days. It is as if the star spends its whole life moving calmly toward an ending, and then, in its final hours, suddenly begins running. And at the bottom of that ladder, waiting, is iron. Iron is where the ladder ends. Not because the star chooses to stop there, but because iron simply does not work the way every fuel before it worked. Every fusion reaction up to this point has released energy. That released energy is what pushed outward, what held the star up. But fusing iron into anything heavier does not release energy. It consumes it. For a star, this is the end of the road. There is no next fuel, no next stage. The core has reached an element that cannot pay for its own support. And gravity, which has been waiting this entire time, patient, constant, never tired, finally gets what it has wanted all along. The collapse that follows is almost impossible to describe in ordinary terms, because almost nothing about it resembles anything ordinary. The core of the star, which moments before was held up by the outward pressure of fusion, begins to fall inward, not slowly, not over hours. The collapse happens at a significant fraction of the speed of light, and it happens in less than a second. Layers of the star that took millions of years to build collapse inward in the time it takes to take a single breath. As the collapse proceeds, temperatures climb into the billions of degrees. The structure of atoms, the same structure we just spent time inside, the nucleus and its surrounding cloud, the empty space that makes up nearly all of an atom's volume, begins to fail completely. Electrons, which under ordinary conditions exist at a respectful distance from the nucleus, are forced inward, forced together with protons. And under that pressure, something happens that does not happen anywhere else in nature, except in places exactly like this. An electron and a proton merge and become a neutron. This happens not to a few atoms, or a few million atoms, but to the entire core of the star, nearly all at once. The structure that once held a star up. That careful architecture of nucleus and electron cloud, the same architecture that lets your hand rest against a table without falling through it, collapses into something almost entirely different. A dense, neutron-rich core where the empty space that once defined matter has simply ceased to exist. This transformation releases an almost unthinkable flood of particles called neutrinos, tiny, nearly massless particles that pass through ordinary matter as though it were barely there. In the moments of a collapse like this, the number of neutrinos released is so large that for a few seconds, the dying star outshines, in pure energy, every other star in the observable universe combined, not in light, in neutrinos slipping outward spacey, through planets, through anything in their path, almost entirely without interacting. Meanwhile, the outer layers of the star, everything above that collapsing core, do not collapse quietly. They fall inward too, briefly, and then slam into the newly formed core, which has, in the span of less than a second, become rigid in a way. Nothing else in the universe is rigid. That collision sends those outer layers rebounding outward in one of the most violent events the universe produces, a supernova. For a short time, days, sometimes weeks, that explosion can outshine an entire galaxy. More energy is released in that brief period than our own sun will produce across its entire multi-billion-year lifetime. And at the very center of all that violence, something survives. Not unchanged, not untouched, but something remains, small, dense, and entirely new. The core that collapsed, the one where electrons and protons merged into neutrons, does not simply keep collapsing forever. At a certain point, it stops, abruptly. The reason it stops has nothing to do with heat, or pressure in the ordinary sense, or any force that resembles the forces we deal with in daily life. It stops because of a rule. A quantum mechanical rule. One that applies to neutrons the way it applies to electrons. A rule that says certain particles simply cannot be squeezed into the same state, no matter how much pressure is applied. This rule is called neutron degeneracy pressure, and it is, in a strange sense, the only thing standing between this newly formed object and complete annihilation into nothingness. Gravity pushes inward with the full weight of a collapsed stellar core. Neutron degeneracy pressure pushes back, not with force, exactly, but with a kind of quantum refusal. Neutrons will not occupy the same space. The rule holds, the collapse halts. And what is left, once the dust settles and the supernova's light begins to fade across the surrounding sky, is the object we have been moving toward all along. Centuries ago, in places without telescopes, without any instrument more advanced than a careful eye and a clear night, people occasionally saw something extraordinary happen in the sky. A point of light that had not been there before, suddenly bright enough to be seen during the day, fading slowly over weeks. They had no framework for what they were seeing, no concept of fusion, or collapse, or neutron degeneracy. They simply recorded it, in whatever way their culture recorded important things, and moved on with their lives. One such event, observed and noted by skywatchers using nothing but careful attention, left behind a remnant that is still there today. An expanding cloud of gas, and at its center, a small dense object, still spinning, still sending out signals centuries later. The watchers who first saw that light could not have known what it would become. They only knew that something had appeared in the sky that had not been there the night before, and that it was worth writing down. The object at the center of that old light, the one that remains, long after the explosion that made it has faded into a quiet, expanding cloud, is what we are now ready to look at directly. What remains, after a death this violent, is something that strains the meaning of the word object. It is small. Around 20 kilometers across, edge to edge, roughly the distance you might cover during an unhurried morning drive, if such a drive were possible across its surface, which it is not. And inside that small space sits more mass than our entire sun contains. The sun, that enormous, slow-burning sphere that our planet orbits, the one whose light is currently warming half the world while the other half sleeps. All of that mass compressed into something city-sized. This is the point where the comparisons that travel from person to person, the spoonful of billions of tons, stop being a curiosity and start being simply accurate. A small piece of this object, smaller than a sugar cube, would outweigh a mountain. Not metaphorically. The matter here is no longer arranged the way matter is arranged anywhere else you have ever encountered. The empty space inside atoms, the space that makes up nearly all of an atom's volume, the space we spent so long inside earlier, that space is gone. What remains is closer to a single continuous nuclear density material, packed edge to edge with nothing left over. And the gravity at the surface of something this dense is difficult to even frame in familiar terms. On Earth, gravity accelerates a falling object at a little under 10 meters per second every second. On the surface of this object, that number is roughly 100 billion times larger. To put it gently, nothing falls slowly here. A small object dropped from a modest height would strike the surface with the kind of energy usually associated with explosions. Not because the object itself is dangerous in any deliberate sense. It has no intentions, no awareness, but because the space around it behaves so differently that ordinary falling becomes something else entirely. And yet, despite all of that violence in potential, the surface itself is, in a strange way, extraordinarily calm. Calm in its geometry, if nothing else. You might expect an object born from a supernova to be jagged, scarred, covered in something resembling mountains and craters, the visible record of the catastrophe that created it. But gravity here is so overwhelming that it does not allow for irregularities. Mountains, if they exist at all, may only be a few millimeters tall, and even that small height represents an enormous structural achievement, a tiny ridge holding itself up against a gravitational pull capable of crushing anything taller almost instantly. Picture a surface flatter than anything you have ever touched. Flatter than glass, flatter than still water. A world where the difference between flat ground and a dramatic landscape feature might be measured in the thickness of a few sheets of paper. Beneath that smooth surface, the material is, by most estimates, among the strongest substances that exists anywhere. Not strong the way steel is strong. Strong in a way that makes steel seem, by comparison, almost soft. A crust held together not by ordinary chemical bonds, but by the sheer continuous pressure of gravity pressing every particle against every other particle with nowhere left to go. And then there is time. This is perhaps the strangest part of all, stranger in some ways than the density or the gravity or the smoothness. Near an object this massive and this compact, time itself does not move at the same rate it moves everywhere else. This is not a metaphor, and it is not a philosophical idea about perception. It is a measurable, physical effect predicted by general relativity and confirmed in smaller forms, even here on Earth. Clocks at higher altitudes run very slightly faster than clocks at sea level because gravity is very slightly weaker the farther you are from the planet's center. Near a neutron star, that same effect becomes dramatic. A clock placed near the surface would run measurably slower than a clock placed farther away, not because the clock is broken, and not because anything mechanical has changed about it. Gravity itself reshapes the passage of time, bending it the way it bends the path of light. And light, too, is affected. Light leaving the surface of an object this dense has to climb out of an extraordinarily steep gravitational slope, and in doing so, it loses energy. Its wavelength stretches, shifting toward the red end of the spectrum. A beam of light that began as one color may arrive, somewhere far away, as another. There is something worth sitting with in all of this. Right now, somewhere in the galaxy, light is leaving the surface of an object like this, stretched by gravity, slowed in its escape, carrying with it the imprint of a place where a second does not mean quite the same thing it means here. That light has been traveling, in some cases, for thousands of years before it reaches any instrument capable of detecting it. It left its source long before the device you are listening on existed, long before the building you are resting in was built. It is arriving now tonight, at exactly this moment, not because anything timed it that way, but simply because that is how long the journey takes, and the journey does not pause for anyone. It arrives whether or not anyone is listening. It arrived for centuries before any instrument existed that could register it, and it will keep arriving long after this particular night has ended, indifferent to all of it, in the same patient way that light has always been indifferent, simply continuing because continuing is what light does. Some of these objects, once they settle into their new existence, do something that seems almost playful in comparison to everything that came before. They spin. When the core of a massive star collapses, it does not simply shrink. It spins faster as it shrinks, the same way a figure skater spins faster when pulling their arms inward. The original star may have rotated slowly, taking days or weeks to complete a single turn. But once that enormous core collapses down to something 20 kilometers wide, all of that original rotation has to go somewhere, and the result is rotation on a scale that is difficult to picture calmly. Some of these objects rotate hundreds of times every second, not hundreds of times a year or a day, hundreds of times in the space of a single second, an object heavier than the sun, turning faster than almost anything humans have ever built. And as they spin, Many of them emit narrow beams of radiation from their magnetic poles, beams that do not always line up with the axis of rotation. So as the object turns, those beams sweep through space the way a lighthouse beam sweeps across a dark coastline. If one of those beams happens to cross paths with Earth, what arrives here is a pulse. Then nothing, then another pulse at an interval so precise that some of these objects rival the best clocks ever built by human hands, drifting perhaps by less than a second across many years of continuous observation. There is something quietly remarkable in that, an object formed in violence, born from the collapse of a dying star, spinning alone in the dark for centuries or millennia, and somewhere in that spinning, a kind of accidental precision emerges, not designed, not intended, simply a consequence of physics, repeating itself with a regularity that took humans a very long time to even notice. Some of these spinning remnants carry something else, too. Magnetic fields so strong that the word strong barely communicates the difference. Earth's magnetic field is useful. It is the reason compasses work, the reason certain birds can navigate across continents. But the magnetic fields around some of these collapsed stars can be trillions of times stronger than Earth's. Fields strong enough, in principle, to distort the shape of an atom itself, stretching it, deforming it in ways that simply do not happen anywhere else. These extreme objects are rare, even among objects that are already rare. Most of these remnants do not reach that level of magnetic intensity. But some do, and when they do, the energy stored in that magnetic field can occasionally be released all at once. A sudden rearrangement deep within the object's crust that sends a burst of radiation outward, powerful enough to be detected from the other side of the galaxy. And then there is what happens when two of these objects find themselves locked together. It is not unusual, across the galaxy, for stars to form in pairs. Two stars orbiting a shared point in space, sometimes for their entire lives. Occasionally, both stars in such a pair are massive enough that both, eventually, become objects like the one we have been describing. Two collapsed remnants, each heavier than the Sun, each compressed into something city-sized, orbiting each other in the dark. At first, that orbit can remain stable for an extraordinarily long time. Hundreds of millions of years, sometimes longer, but every orbit, no matter how slowly, loses a small amount of energy. The two objects spiral inward fractionally with each pass. Slowly at first, so slowly that for most of the system's existence, nothing about it seems to be changing at all. But eventually, the spiral tightens. The orbits shorten from years to days to hours to minutes, and finally to mere seconds, the two objects whipping around each other faster and faster as they draw closer together. And then they meet. When two objects like this collide, the result is something that, for most of human history, would have been entirely beyond imagining. For a brief moment, seconds at most, the collision can outshine entire galaxies. The matter torn loose during that collision is flooded with an enormous number of free neutrons, and under those conditions, atomic nuclei rapidly absorb them, building in an instant some of the heaviest elements that exist in nature: gold, platinum, elements that on Earth sit quietly in jewelry boxes, in electronics, in the thin wiring of countless ordinary devices, elements that, by most current understanding, were forged in exactly this way. Not gradually, the way most elements form inside ordinary stars, but suddenly, violently, during the collision of two long-dead stellar remnants, somewhere across the galaxy, long before our solar system existed. In one such collision, detected not through light alone, but through a faint ripple in the structure of space itself. A distortion so small it changed the length of detectors on Earth by a fraction smaller than the width of an atomic nucleus. Astronomers confirmed, for the first time, that this is genuinely how it happens. Two neutron stars, spiraling together for what may have been billions of years, finally meeting, and in that meeting, scattering the raw material for gold across the surrounding space. It is worth letting that settle, quietly, for a moment. Some of the atoms in the room around you, in a ring perhaps, or in the wiring of the device resting near you, may have been forged in exactly this way, carried across unimaginable distances over unimaginable spans of time, from a collision between two objects that no longer exist as separate things, into the quiet, ordinary places where you now rest. There is a particular kind of stillness that comes from realizing how much of what surrounds you was made somewhere else. Not made in the sense of manufactured or built, but made in the deeper sense. The atoms themselves, the raw material, assembled under conditions that no factory, no laboratory, no human process could ever come close to replicating. Forged in the brief, violent moments when two collapsed stars finally meet, after spiraling toward each other for longer than any human structure has stood. It is strange to think that gold, something so often associated with permanence, with things meant to last, with rings exchanged as promises meant to outlive the people making them, might owe its existence to one of the most sudden and catastrophic events the universe produces. A promise of permanence made from material born in an instant of total destruction. Perhaps that is not a contradiction exactly. Perhaps it is simply how things are. The calm and the catastrophic, it seems, are not always opposites. Sometimes the calm is what comes after. The long, quiet aftermath of something that was at the time anything but calm. There is something in that worth sitting with, gently, without needing to resolve it. The same physical laws that govern the unimaginable density of a neutron star. The same laws that bend time near its surface, that stretch light leaving it, that hold its matter together against gravity, through nothing more than a quantum rule about particles refusing to share the same state. Those same laws are operating right now, quietly, in the room around you, in your body, in the simple fact that you are resting against something solid and not falling through it. It is the same gravity. Not a different version of it, not a smaller cousin of it. The same force, the same equations, scaled down so gently that it becomes almost invisible. The force that crushes matter into something city-sized, heavier than a star, is the same force that is, at this moment, holding you gently in place. There is something almost reassuring in that, if you let it settle. The universe does not seem to operate by different rules in different places. The strangeness of a neutron star and the ordinariness of a quiet room are not separated by different laws, only by degree, by how much and how concentrated and how far from anything familiar. Perhaps that is part of what makes objects like this so difficult to fully absorb. They are not exceptions to how the universe works. They are simply the universe, doing what it always does, but pushed to an extreme that human experience never has to encounter directly. In ancient Egypt, long before anyone had a name for gravity, or fusion, or the particles that make up an atom, a person might have lain outside on a warm evening and looked up at a particular patch of sky. The same patch of sky, in fact, that someone tonight might also be looking at in some other part of the world at some other hour. That person in ancient Egypt would have had no way of knowing that somewhere in that patch of sky, hidden among the ordinary points of light, there might have been a star already living out its final centuries, already, in some sense, beginning the long process that would end in collapse, in a supernova, in an object spinning quietly in the dark, long after that observer, and everyone that observer ever knew, had lived and died. The geometry of the sky has not changed much since then. The stars are, for the most part, in roughly the same places. What has changed is only what we know is hidden among them. That observer was not wrong about anything they saw. The sky looked the way it looked. The stars were where they were. They simply did not yet have a way to ask what some of those points of light might eventually become, or what some of them might already secretly be. We are, in some ways, still that observer. We have better instruments now, better questions, but the sky itself has not become less mysterious by becoming better understood. If anything, it has become more so. Because now we know how much is happening, quietly, in places we cannot see directly, hidden behind ordinary-looking points of light. Perhaps that is enough for tonight. Not an answer, exactly. Neutron stars do not resolve into answers easily, but a kind of settling. A sense that the universe is larger and stranger than it appears, and that this strangeness is not separate from the quiet, ordinary moment you are in right now. It is simply continuous with it. The same fabric, stretched to different extremes. Right now, you are still resting against something solid. The same mattress, or couch, or floor that you were resting against at the beginning of all this. Nothing about that has changed. Gravity is still holding you there, gently, the way it has held you there every night of your life, without effort, without announcement. It is strange to think that the force doing that, the quiet, mild, almost unnoticeable pull keeping you in place, is the same force we have spent this entire time describing. The same force that, somewhere else, in some other part of the galaxy, is holding together an object so dense that a piece of it smaller than a sugar cube would outweigh a mountain. Here, it is gentle enough to go unnoticed for an entire lifetime. There, it is strong enough to crush atoms into something new. It is the same thing, only the scale is different. Think back for a moment to that childhood memory, lying outside on some ordinary evening, looking up at a sky full of points of light, none of them meaning anything in particular, yet just light, just background. Part of the shape of the night, the way the ceiling of a room is part of the shape of a room. At the time, there was no way to know that some of those points of light were stars already living out their final years. No way to know that, hidden among the steady, familiar ones, there might have been a star quietly approaching the end of its fusion ladder, working its way down through hydrogen and helium and carbon toward an ending that would not arrive for a very long time, but was already, in some sense, written into how massive that star happened to be. None of that mattered at the time. It still doesn't, really. The sky looked the same either way. The points of light were just as steady, just as quiet, just as easy to drift off beneath, and the spoon. The one sitting in a drawer somewhere, yours perhaps, or one very much like it. An ordinary object, metal, lightweight, the kind of thing that gets used and put away without a second thought, dozens of times, without anyone ever considering what it might mean to fill it with something else. Somewhere, right now, there is material that would fill a space like that and weigh more than anything that has ever been weighed by anyone, anywhere, for any reason. Not as an idea, as an actual fact about an actual object existing in an actual place, spinning, quietly, in the dark, the way it has been spinning for longer than anyone has been alive to notice. And none of that changes anything about the spoon in the drawer. It is still just a spoon, ordinary, quiet, waiting to be used again the way it always has been. There is something gentle in that contrast if you let it settle slowly. The universe contains both of these things, the ordinary spoon and the impossible density it can be compared to, without any contradiction. They simply exist at different scales, governed by the same rules, never needing to meet. The night outside, wherever you are, continues the way it always has, quiet, steady, mostly dark, with a scattering of light here and there, some of it from streetlights or windows, some of it from much farther away, light that left its source a very long time ago and is only now arriving at this exact moment for reasons that have nothing to do with anyone listening. That light does not know it is being received. It does not know anything at all. It simply continues the way it has always continued, the way gravity continues, the way the slow turn of a distant, dense, spinning object continues, unhurried, indifferent, and somehow, despite everything, oddly steady. You are still here, still held gently by the same force that holds together the strangest objects in the galaxy. And the night goes on the way it always does. Somewhere, far beyond anything visible tonight, a small point of light is still turning. It does not know how far it is from anything. It does not know that it is rare, or strange, or difficult to picture. It simply turns the way it has turned for a very long time, sending its quiet pulse outward into the dark in every direction at once. Some of that light is on its way here now, has been for longer than anyone can easily imagine. It will keep arriving long after tonight, long after this particular thought has faded, long after the room around you has gone fully quiet. There is no need to follow it any further. The star does not need anyone watching. It spins because that is what it does. The light travels because that is what light does. And somewhere, very far away, in the gentle dark between one star and the next, that is simply how things continue. The night holds its shape, quiet, steady. Unbothered, somewhere above, hidden among the ordinary points of light, something impossible is turning slowly in place. And here the night settles a little further. The room grows quieter, the breathing slows. Far away, the star turns on.